All right, in this video, we're going to talk about suggested homework problems from 5.4, and we'll be covering the topics of differentiation and integration of exponential functions. But first, we'll have a review of exponential functions from pre-calculus and solving exponential and logarithmic equations. Let's go ahead and look at number 3. E to the ln of x is equal to 4. Because these are inverse functions, when I compose them, I get x, and it simplifies to x is equal to 4. Number 5, e to the x is equal to 12, and I'm going to take the natural log of both sides. And so this is going to, again, because these are inverse functions, this will become x, and x is exactly equal to ln of 12. And when I approximate that to 3 decimal places, 2.485, look at number 7, which is 9 minus 2 e to the x equals 7. So when I subtract 9 from both sides, negative 2 e to the x is equal to a negative 2. Divide by negative 2. E to the x is equal to 1. And when I take the ln of both sides, x is equal to 0. Or I could have used my one-to-one property that e to the x is equal to e to the 0 and set the exponents equal to each other since the bases were equal and x would equal 0 that way. Let's look at number 9. Save the information from number 5. It's going to help you with number 9. So or with some of the upcoming problems, maybe not number 9 quite yet, but e to the negative x is equal to 3/5. E to the x is equal to 5/3 when I take the reciprocal of both sides, raise each side to the negative first power here. When I raise a power to a power, I multiply the exponents. The reciprocal of 3/5 is 5/3. Take the natural log of both sides. And x is equal to ln of 5/3, which is 0.511. Let's look at number 13. ln of x is equal to 2. So x is equal to e to the 2, and that's going to be 7.389. Hang on to that. That's the one that will show up again. 15. ln of x minus 3 is equal to 2. So e to the ln of x minus 3 is equal to e to the 2. See, there it is again. So x minus 3 is equal to e to the 2. X is equal to e to the 2 plus 3, which is approximately, if we add 3 to that, that's 10.389. And then number 17 is again going to be based off of number 13. So ln of root x plus 2 is equal to 1. So this is really x plus 2 raised to the 1/2 power. And that 1/2 can come in front of the log through log properties. And I'm going to multiply by 2 to get rid of the fractional coefficient. And then we have e to the power of and e to the power of. So x plus 2 is equal to e to the 2. So x is equal to e squared minus 2. Coming back here, x is approximately 5.389. Let's move on now to number 19. And 19 wants us to sketch a graph of y equals e to the negative x. So this is an exponential decay function. Still goes through 0, 1, and it's going to go through 1, 1 over e, 2, 1 over e squared, and it's going to approach y equals 0 as I come to the right here. And it's going to get smaller and smaller, closer to 0, but not ever get there. And at negative 1, it's going to be at e. And then at negative 2, it's going to be at e squared, which is way up here, and it keeps growing exponentially that way. So if you want to see that, a better graph of that in the calculator, then there it is. It's an exponential decay function, as opposed to the exponential growth function, which I'll put in y2, which is e to the x. And you can see they both go through 0, 1, but exponential growth rises to the right, exponential decay falls to the right and approaches that horizontal asymptote. They both have one-sided horizontal asymptotes and are unbounded in the other direction. So moving on now to number 33. 33 asks us to find the derivative of y equals e to the 5x. And we'll use the rule that the derivative with respect to x of e to the u is equal to e to the u times u prime. So u is 5x and u prime is 5. This is e to the u. So y prime is e to the u times u prime is e to the 5x times 5, or 5e to the 5x. 39 is the next problem. So 39 says y is equal to e to the x times ln of x. So I have a u times a v, where u is equal to e to the x and v is equal to ln of x. U prime is equal to e to the x. We learned in 5.1 how to differentiate this as 1 over x. And we know our product rule that y prime is u prime v plus v prime u. So y prime is e to the x, ln of x plus 1 over x times e to the x. I have a common factor of e to the x that they like to take out in exponential functions, like so. So we'll go ahead and do that. And let's look now at number 41. The reason we like to factor out the exponential piece is when we are going to do the first derivative test or second derivative test or something like that. Remember that exponential piece can approach 0 but can't ever get there. So we don't really need to consider that piece when we're finding zeros of our first or second derivative. We need to consider this other factor and don't need to consider the exponential piece that can never be 0 unless something is added or subtracted to the exponential factor. Like if I had e to the x plus 1 as a factor, then it could possibly, not plus 1, e to the x minus 1, then it could possibly be equal to 0 at some point. All right, let's look at 41. Y is equal to x plus 1 squared e to the x, where I have a u times v situation where u is equal to x plus 1 squared, and v is equal to e to the x, and u prime is 2 times x plus 1. I'm going to leave that factored for a second. V prime is e to the x, y prime is u prime v plus v prime u. So y prime is 2 times x plus 1 times e to the x plus And then we have x plus 1 squared e to the x. So factoring out what is common, 2 is not common, x plus 1 is common, e to the x is common. I'm left with 2 plus another x plus 1 here, and the e to the x was common and came out, so y prime is e to the x times x plus 1 times x plus 3. Let's look now at number 43. G of t is equal to e to the negative t plus e to the t raised to the third power. So this is u to the third power, with u being equal to e to the negative t, e to the negative t plus e to the t. U prime is going to be negative e to the negative t plus e to the t. So g prime of t will be 3u squared times u prime when I use the power rule. G prime of t is equal to 3 times u squared times, and I'll write this as e to the t minus e to the negative t as subtraction, like so, and I'll leave it just like that. That's sufficient for the derivative for me. 45. Y is equal to ln of 2 minus e to the 5x. So this is ln of u, where u is equal to 2 minus e to the 5x. U prime is 0 minus 5e to the 5x, or a negative 5e to the 5x. Y prime is 1 over u times u prime is negative 5e to the 5x over 2 minus e to the 5x. Yeah. Moving on now to number 47. Y is equal to 2 over e to the x plus e to the negative x. I'll make this 2 times e to the x plus e to the negative x raised to the negative first power. And call this y equals 2 u to the negative first, where u is equal to e to the x plus e to the negative x. That makes y prime equal to a negative 2 u to the negative second times u prime. U prime is e to the x minus e to the negative x. So y prime will be a negative 2 u prime over u squared. Negative 2 times u prime over u squared. Let's look now at 49. Y is equal to e to the x plus 1 over e to the x minus 1. And this is u over v. U is e to the x plus 1, and v is e to the x minus 1. U prime is e to the x, and v prime is also e to the x. Y prime is going to be u prime v minus v prime u all over v squared because of the quotient rule. So that will be e to the x times e to the x minus 1 minus e to the x times e to the x plus 1 over e to the x minus 1 quantity squared. So y prime will be e to the 2x minus e to the x minus e to the 2x minus e to the x over e to the x minus 1 quantity squared. E to the 2x minus e to the 2x is 0. And -1 and -1 is -2 e to the x over e to the x minus 1 quantity squared. So now at 51, says y is equal to e to the x times sine of x plus cosine of x, which I'll call u times v, with u equal to e to the x and v equal to sine of x plus cosine of x. U prime will be e to the x and v prime will be cosine of x minus sine of x. My y prime will be u prime v plus v prime u, since it's a product rule. Y prime is e to the x times sine of x plus cosine of x plus v prime u, e to the x times cosine of x minus sine of x. Y prime is equal to e to the x sine x plus e to the x cosine of x plus e to the x cosine of x minus e to the x sine of x, and e to the x sine of x and negative e to the x sine of x zero each other out. Y prime is a 2 e to the x cosine of x. Let's look at 55 now. We'll be finding the equation of the tangent line. F of x is equal to e to the 3x, and we'll be at the point 0, 1. So f of 0 is 1 is what they're letting us know there. F prime of x will be 3e to the 3x. So f prime of 0 is 3e to the 3 times 0, or 3e to the 0, which is 3 times 1, which is 3. So I have a point, and this is specifically a y-intercept. So I don't need to use point-slope form. I can just use slope-intercept form here. Y is equal to mx plus b. Let's look now at number 57. Is y is equal to e to the 3x minus x squared, given the point 3, 1. And y prime is going to be, write this part down, multiply it by the derivative of the exponent, and then we'll evaluate that at the x value that's given. And we know that this piece is 1 times 3 minus 6 is going to be a -3 for our slope. So y minus y1 is equal to m times x minus x1. Y minus 1 equals -3x plus 9. Add 1 to both sides, and I have y is equal to a -3x plus 10. So look now at number 59. Number 59 says f of x is equal to e to the -x ln of x at the point 1, 0. So f of x is equal to u times v, where u is e to the -x and v is equal to 1 over x. U prime is a -e to the -x. V prime is equal to, why did I say that? That's the derivative. V is ln of x and v prime is 1 over x. I was thinking ahead. So f prime of x is equal to u prime v plus v prime u. F prime of x is equal to a negative e to the negative x ln of x plus e to the negative x times 1 over x. We'll factor out the e to the negative x, and we'll get 1 over x minus ln of x. Let's stick in 1. So e to the negative first times 1 over 1 minus ln of 1 is equal to e to the negative first times 1 minus 0. F prime of 1 is equal to e to the negative first times 1 is e to the negative first for our slope. So y minus y1 is equal to m times x minus x1. Y is equal to e to the negative first x minus e to the negative first, or 1 over e x minus 1 over e. Let's continue now with number 67. And it asks us to find the second derivative. 67 is f of x is equal to quantity 3 plus 2x times e to the negative 3x. So f of x is equal to u times v. And so f prime of x will be u prime v plus v prime u. And let's just go ahead and see what the second derivative would be. So taking the derivative of the first part, leave the second part alone, plus leave the first part alone and differentiate the second part, plus differentiate the first part, leave the second part alone, plus differentiate the second part, leave the first part alone. So f double prime of x here is u double prime plus 2 u prime v prime plus v, let's see, u double prime v plus v double prime u. So let's go ahead now that we've done that generically, and let's define u as 3 plus 2x and v as e to the negative 3x. U prime is 2, u double prime is 0, v prime is negative 3e to the negative 3x, v double prime is 9e to the negative 3x, and let's plug and chug here. So f double prime of x is equal to 0 plus 2 times 2 times negative 3 e to the negative 3x plus 9 e to the negative 3x times 3 plus 2x. F double prime of x, look for common factors if they exist. Well, let's distribute here. 4, this is negative 12 e to the negative 3x, and this is 9 times 3 is 27 e to the negative 3x, and then we have plus 18x e to the negative 3x. So we have like terms here. We have 27 minus 12 is 15 e to the negative 3x plus 18 x e to the negative 3x. I see a common factor of 3. I see a common factor of e to the negative 3x. That gives me 5 plus 6x, or 6x plus 5. And That's it for that problem. Let's move on now to number 71. Let's find relative extrema and points of inflection. F of x is equal to e to the x plus e to the negative x over 2. We'll be talking more about what that function defines here and a little bit later in this chapter. You may recognize that function, you may not, but it'll be a special function that we'll talk about later. Right now, we'll just deal with it the way that it's written. So relative extrema. So f prime of x is 1/2 e to the x minus 1/2 e to the negative x, or 1/2 of e to the x minus e to the negative x, which is the same thing as e to the x minus e to the negative x over 2. This is also a special function that we'll talk about later in this chapter. We're going to set that derivative equal to 0. So that's e to the x minus e to the negative x is equal to 0. Going to factor out e to the negative x, get e to the 2x minus 1 is equal to 0. And then e to the negative x is never 0, so I'll let e to the 2x minus 1 equal 0. E to the 2x is equal to 1. 2x is equal to 0. X is equal to 0. This is e to the 0, so I'm setting the exponents equal to each other there, or taking the ln of both sides, whichever you prefer. So there is something going on that's interesting at 0. This was all defined for all real numbers. So, and my derivative is defined for all real numbers. When I have a negative exponent, this is the small number, this is the big number. They're both positive numbers, so small positive number minus big positive number, that's going to be negative and decreasing. And then when I have it the other way around, positive exponent and negative exponent, big number minus small number is positive and increasing. So that means that there's a local min at x is equal to 0. F of 0 is equal to e to the 0 plus e to the 0 over 2. F of 0 is 1 plus 1 over 2, or 2 over 2 is 1. So local min at 0, 1. And let's show you that function so that you can see that there is a local min at 0, 1. So that's e to the x plus e to the negative x divided by 2, and zoom 6, and second calc minimum here to the left and there to the right. And that's basically 0 to the calculator. There's 7 zeros in front of that and 1. That's why we find it with calculus first and then use the calculator to check, and don't go strictly off of what the calculator says. All right, moving on to integration problems with number 91. And we'll be using the technique that e to the u du is equal to e to the u plus c. We may be using some other techniques as well, but that's the main one that we learned in this section. So integral of e to the 5x times 5 times dx, and u is 5x and du is 5 dx. So I have e to the u du, which is e to the u plus c. So that's e to the 5x plus capital C. Remember to use your capital C for your constant of integration in WebAssign. It is case sensitive. All right, 95. Integral of 2x plus 1 e to the x squared plus x dx. So my u is my exponent on e. My du is 2x plus 1 dx. So this is e to the x squared plus x times 2x plus 1 dx if I rearrange, which is e to the u du, which is e to the u plus capital C. So this is e to the x squared plus x plus c. Moving on to number 97. 97 is integral of e to the square root of x over the square root of x dx. So u has to be the exponent on e, and so I'll call that x to the 1/2. Du is a 1/2 x to the negative 1/2 dx, or a 1/2 square root of x dx. So we have e to the root x times root x down here, 1. Let's change my color. Divide by 2, multiply by 2 to make 2 integral e to the u du show up, which will be 2 e to the u plus c. So that's 2 e to the root x plus c. Let's look at 105. 105 is integral 5 minus e to the x over e to the 2x dx. Since the denominator is a monomial, going to use my power rule here, bring my negative exponent up like this, e to the negative 2x times 5 minus e to the negative, or 5 minus e to the x dx. And I'll distribute that to be 5e to the negative 2x minus e to the negative x dx, and I'll split my intervals now. Integral of 5e to the negative 2x dx minus integral e to the negative x dx. I'll pull my constant multiplier out front. Leave myself some space here for my du, and minus e to the negative x, leave some space here for my du, and I'll put the invisible 1 right there to be helpful in just a second. So in this first one, u is equal to a negative 2x, so my du is a negative 2 dx. So multiply by negative 2 on the inside, divide by negative 2 on the outside. If u is e to the negative x, du is a negative e to the negative x dx. So multiply by negative 1 on the inside, divide by negative 1 on the outside. I could have just pulled that negative 1 inside as well, but trying to stay consistent here. Negative 5/2 integral of, let's call this b, just be different here, e to the u du plus e to the b dv, like that. So this is -5/2 e to the u plus e to the v plus c. I get -5/2 e to the -2x plus e to the -x plus c. I knew what I was trying to do and then didn't write down what I was saying. So I apologize there. V is -x and dv is -1 dx. And so there's my e to the v, dv, and my adjustment for it. 109. I will say that differentiation and integration of exponential functions just kind of becomes automatic. At some point, you stop writing all the little steps, which is maybe why I messed up that step, but wrote the right thing. All right, evaluate the definite integral. So u is a -2x and du is a -2 dx. -2, multiplication on the inside, -1/2 on the outside. I have a -1/2, change my bounds. So u is still 0. Upper bound -2 times 1 is -2. E to the u du. Those bounds are backwards. So I need to go -2 to 0, and that changes the sign of the coefficient out front. E to the u du is a 1/2 e to the u evaluated from -2 to 0, meaning we have 1/2 of e to the 0 minus e to the -2, which will be 1/2 of 1 minus 1 over e squared, or 1/2 of e squared minus 1 over e squared. And that's that. Let's look at 111. Zero to 1 of x e to the -x squared dx, where u is a -x squared, du is a -2x dx. So I need a -2 and a -1/2 to balance it. -1/2, 0 to 1, e to the -x squared to -2x dx will be -1/2 e to the u du. Let's change my limits. That's still 0. That's a -1. So I need this to be a positive 1/2, -1 to 0 of e to the u du is 1/2 of e to the 0 minus e to the -1 is 1/2 of 1 minus 1 over e, which is 1/2 of e minus 1 over e, or e minus 1 over 2e. So go 113. 113. 1 to 3 of e to the 3 divided by x over x squared. U is 3 divided by x, or 3x to the negative first. U prime is a negative 3x to the negative second, or a negative 3 over x squared. So 1 to 3 e to the 3 over x times x squared dx, and I need a negative 3 here, which means I need a negative 1/3 out there to balance it out. So I have negative 1/3 e to the u du, and limits of integration are going to be, when I stick 1 into my definition of u, I get 3, and when I stick 3 into my definition for u, I get 1, so those are backwards. So 1/3, 1 to 3 of e to the u du is 1/3 of e cubed minus e to the first is e over 3 times e squared minus 1, which is e times e plus 1 times e minus 1 over 3. Scroll on down here to 125, and we're asked to find area of the region. So 125 says y is equal to x e to the negative x squared over 4, y equals 0, x equals 0, x is equal to root 6. Okay, I'm going to need a little bit of help graphing this from my graphing calculator. So x second e to the negative x squared divided by 4, zoom 6. That looks kind of funky there. X is going just from 0 to second square root of 6, and maybe I can make these increments kind of small here. All right, so it's going to go, appears it's going to go through 0, 0, and then it probably, it doesn't look like it goes quite to the x-axis there again. There's a little bit of space right there still. I'm interested in this shading in here. So the main thing is the height of each rectangle here is this upper function. So I can just integrate from x e to the negative x squared over 4 dx and go from x is equal to 0 to x is equal to the square root of 6, defining u to be negative x squared over 4. Du will be a negative 2x over 4, or a negative x over 2, a negative 1/2 x dx, dx, dx. So negative 1/2 is my multiplier that I need. On the inside, negative 1/2, which means I need a negative 2 on the outside. So negative 2 integral of e to the u du, and when I stick 0 in, that's 0. When I stick root 6 in, that's negative 6 over 4, or negative 3/2. Those limits are backwards, so this is going to become 2 from negative 3/2 to 0 of e to the u du. So that is 2 e to the u evaluated from -3/2 to 0 is equal to 2 times e to the 0 minus e to the -3/2 is equal to 2 times 1 minus 1 over e to the 3/2 is 2 times e to the 3/2 minus 1 over e to the 3/2. And let's evaluate that to get the approximate area. So y equals n over d, 2 times e to the 3/2 minus 1 for my numerator, and e to the 3/2 for my denominator gives me approximately 1.554 for my area of the region. And that's it for this video. We'll come back next time and talk about suggested homework problems from section 5.7. See you for the next video.